Hello kids and Happy New Year. Welcome back from Christmas break. I'd like you to open your notes to page 8. It's the big purple packet, and if the sub could pause this video while everybody's finding their note packet, taking it out and opening it to page 8. Once everybody's got their packet open, we'll begin. So pause the video. All right, so this is Mrs. LaRude coming at you from down the hall for Mrs. Peterson's student. She couldn't be here today. She'll be gone for a couple days. So I have recorded the notes for you. They're the same note packet you have, so no worries. Anyway, first thing we're going to start doing is a little review for the final, because that's coming up here at the end of the semester. We're going to start off with number 1, just a simplifying of polynomials. I didn't leave a whole lot of space on these notes. I'm sorry about that, but we'll squeeze it on in here. So first of all, when we're subtracting polynomials, what you have to remember is this negative needs to get distributed in to every single term. So we got to do a little hippity-hoppity distributive property here and hop that negative on in. You can think of it as a -1 times every term, or you can just think of subtracting every term. Either way, a negative times a negative is a positive. And when we subtract a negative, we end up adding. So either way you think of it, what that negative out front is going to do is cause all the signs to change. Every 2 negatives will make a positive. So this first one I'm not going to mess with. But the second one, when I hop that negative in, I'm just going to try to squeeze it in right under here. A negative times a negative will give me a positive 3x cubed. And then on the next one, a negative times a negative will give me a plus x squared. And then on the next one, the negative times the negative will give me a plus 4x. And again, on the end, a negative times a negative is going to give me a plus 1. So all the signs changed. So now what I need to do here is I need to add the first polynomial with the second polynomial, because I've now got it all addition. So I've got x cubed right here, and I'm adding 3 more x cubes. 1x cubed plus 3x cubes gives me 4 of those. Make sure you don't make that x to the 6th. So when we add, we're combining like terms. So we'd have 4x cubes. On the first polynomial here, I have a minus 2x, but then over here, I am adding 4x. So those are going to combine. You'll also notice, though, that the first term didn't have any x squareds. So this x squared in the second one is going to hang along here for the ride as well. So I'm going to have a plus x squared. We like to go in order of the exponents. It's called standard form. So I'm doing my cubes first, then my squareds, and now my x's. I've got minus 2x's plus 4x's, which gives me positive 2x's. And then to finish it off, I've got a plus 1 in the first polynomial. I'll go green here so you can see it. And then when I distributed my negative in, I ended up with another plus 1. So this will wrap up here with a plus 2. And that's how we subtract. We hop that negative into every term. Next, number 2, x squared minus 4x minus 1 is called a. Well, let's see if we remember what this is called. When we have a second degree, we call them quadratic. And when we have 1, 2, 3 terms, we call it a trinomial. So that is a quadratic trinomial, which we spent all of Chapter 9 graphing and finding the vertex and all that good stuff. And its graph was called a parabola. Not a parabola, a parabola. So that's just a little review for the final. Now we're going to review a little bit of what we did before Christmas. So the key to Chapter 10 is really, it's all about square roots. And the key is knowing who your best friends are in the square root world. And we call those things perfect squares. And so let's list the first 15 perfect squares. They don't get memorized, they get created. 1 times 1 is 1. 2 times 2 is 4. 3 times 3. 4 times 4, 5 times 5, 6 times 6, 7 times 7. Notice I'm not memorizing them. I'm just creating them by squaring every counting number. I'm at 8 times 8, 9 times 9, 10 times 10 is 100. 11 times 11 is 121. 12 times 12 is 144. 13 times 13 is 169. One of the hardest ones to remember is 14 times 14, but you'll notice all it does is swap the 6 and the 9 that you got in the 13 times 13, so that's an easy way to remember it. And last up, 15 times 15 is 225. These are our first 15 perfect squares, and their roots are the counting numbers. That's why we call them perfect squares, because the square roots of all of these would be the numbers 1, 2, 3, and we don't need to list the roots, but the square root of this would be 1, 2, 3, 4, etc., all the way on down to the square root of 225, which is 15. What it's important to know is that any number in between those, like 10 is a super nice number, our whole number system's based on it, but nobody knows the square root of 10. It goes on forever and it never repeats. So, and it falls right in between here. So I know it's between 3 and 4, the square root of 10, probably closer to 3, but I don't know what it is exactly. So keep that in mind, that anything in between those, nobody knows. We can simplify some of them, but we don't know what they are for sure. And so let's talk about what a radical expression is. A radical expression is just something that lives under a radical symbol. It doesn't have to actually be a square root. It could be a cubed root or a fourth root, but we call a radical expression anything with that symbol living above it. And to simplify a radical expression means to break it down. It's kind of like simplifying fractions. I'm going to write this in green. Don't put this in your notes for a second. When you were in elementary school, you learned how to simplify fractions. Don't write this down. And you would find the biggest number that goes into both. And sometimes you would miss that biggest number and you'd say, oh, it's 2/4. And although that's not incorrect, it's not in what we call simplified form. We have to break it all the way down to its best, most simple form, which for fractions, I mean, that's so obvious to you guys because you've been working with them for so long, but that's really what we're doing with square roots. We are breaking them down to their simplest form. And what it means is any one of these perfect squares that's basically hiding in your number, to simplify, you pull it out and you break it down. So really what it means to simplify a radical expression, in its loose terms here, is to find any perfect square. I'm going to go draw an arrow up to there. Any one of those besties up there, find any perfect square that's hiding, really that's a factor. I always say, though, that it's hiding out in there and you're kind of on a search and rescue mission to go find out what it is. Find any perfect square that is a factor of the number that's under the radical. Let's even go like that. And pull it out. Well, that might seem kind of weird, but let's go over here and review that because you did that before Christmas a lot. So when we're asked to simplify, what we do, let's take a really easy one, like the square root of 20, is we look for, is there any one of those perfect squares that's kind of hiding out in my number? And you might say, oh, 2 and 10 are in 20, but neither one of those are in my list of perfect squares. So if I break it into 2 and 10, I take one number I don't know the root of, and I break it into 2 I don't know the root of. So we find that 4 that's hiding out in there, and we say, well, it's root 4, root 5. And then we simplify that, because the square root of 4 we know. Root 20 and 2 root 5 are identical. They're just in different forms, and this is considered simplified. So let's go down to the bottom here. It says, which of the following are simplified? And this one is yes. And this one's kind of tricky because it depends on what x is, but because you don't know what x is, you would say that's simplified as well. This one, remember before Christmas, we aren't allowed to leave those roots in the denominator, and we talked a lot about why not before Christmas break, but this is a no-no. So no roots on the bottom. That's also part of simplification. We find those perfect squares and we pull them out, and then let's even write back up here, go back up here. No roots on the bottom either. Historically, that caused them huge problems with trying to figure out what answers were because they didn't have calculators. And to divide by that root meant long division by decimals, which was icky. Yeah. Anyway, so no roots on the bottom are allowed. We'll talk about how we get those off of there. You already did before Christmas, but. And this one, you might say, yep, that's done. It's not, because remember what I said up here, root 20 has a perfect square in it. So this one is not simplified because root 20 has a 4 hiding out in it. And anything that has one of those, you got to kind of search and rescue, find it, and break it down. So let's go review a little bit of simplifying. We are looking for the biggest perfect square that goes into 160. You might say, oh, it's even. I'm going to do 2 and 80. Well, that's lovely, except neither one of those is a perfect square. You might say, well, I'm going to do 4 goes in there for sure, which it does. Watch. 4 times 40 equals 160. But remember, my goal is to find the biggest perfect square. And if I say it's root 4, root 40, that equals root 60, I haven't found the biggest. And here's how I know that. Because 40 still has a 4 hiding in it. So it's kind of like that fraction deal, saying 4/8 simplifies to 2/4. True, but that's not its best form. So we need the biggest perfect square. And I'm seeing a big old 16 in there 10 times. And I know that's the biggest because 10 doesn't have any of those perfect squares in it. So my answer would be 4 times the square root of 10, because the square root of 16 is 4. Let's talk about root 72. Usually what kids will do with root 72, I'll put it with my naughty pen down here, is they'll go root 9, root 8, which is a really good thought because root 9 is a perfect square. But again, root 8's not done. It still has a 4 in it. So that means there's a bigger perfect square and you need to find it. And you would eventually stumble upon 36 goes in there twice. And this simplifies down to 6 root 2, and that we did before Christmas. Also before Christmas, we dealt with the square roots of variables. And if I were to ask you, what's the square root of 3 squared? You might say, well, 3 squared is 9. I'll take its root. I get a 3. I could say, well, what's the square root of, say, 19 squared? You might say, I don't want to go do 19 squared. You don't have to, because these are inverse operations. They undo each other, kind of like add, subtract, multiply, and divide. When you square root a squared term, they undo each other. So this is just 19. The square root of, anything squared, like, I don't know, maybe make it 9,999 squared. You don't really need to know what that is squared because those operations undo each other. So what that allows us to do, to do with the variables is to notice that anything, when you root and square it, they undo each other. So this is just x. Well, what about if we bump up the exponent on each of these? Well, we're still trying to simplify it, and every 2 of them cause an x to pop out of the root. So the easiest thing to do is just take that 3 and divide it by 2, and you'd be able to pull 1 x out, but 1 would remain in. So kind of think of it as like division with a remainder. 1 x would come out, 1 would stay in. Same right here. If I divide this by 2, I get 2 would come out, and I won't have a remainder, so none stay in. Divide 5 by 2. And you wouldn't do it by hand, you do it in your head, but just so you can see it. 2 x's would come out, because there's 2 2's in 5. But I would again have 1 that would remain in. So I'd go x squared root x. So notice the pattern here. The last one, 2 goes into 6 evenly 3 times. You'll notice the pattern that every time we're rooting an even, we're getting nothing left under the root. All we do is divide it by 2, and so for the evens, we just get x to the number divided by 2. That's what pops out of there. Here is x to the 6 over 2 is 3. If I said, what's the square root of x to the 10th? 10 divided by 2 is 5. So it just will pop out 5 x's exactly. You could write it all out and say x to the 10th is x squared times x squared 5 times. which is legal, but each one of these pops out 1x. So there's your x to the 5th. Every odd one has a remainder. For the odd ones, we get x's coming out to the number divided by 2. That's how many, but we always end up with 1 in there. So now let's combine those two thought processes. Hang in there with me. I know it's getting a little long, but we're just coming back from Christmas, so wake up! All right, so now we're going to combine both of those skills. Let's go and simplify completely. 3 times the square root of 75, x cubed. This is going to be so much fun. The 3, what do I do with that? Absolutely nothing. It stays right out front. The number 75, what do I do? Well, I see if I've got one of those perfect squares hiding in there. But Mrs. LaRue, I forgot my perfect squares. Then go write them up here. 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6. They should always be creatable. Is that a word? I don't know. Anyway, you should spot this one hiding out in your 75, and you're going to break that up. You're going to say, well, that would be root 25, right? Coming out of there, and it'd be 25 times 3 if you even want to leave that all under the root for now. Likewise, my x cubed is going to get simplified also. So now what I'm going to do is go pop out my perfect squares. I know the square root of 25 is 5. This 3 is just hanging along from the beginning. I do not know what the square root of 3 is, so it stays living under my root. We just talked up here about how with these odd powers, we say how many 2's go in there. And you'd say, well, 2 goes into 3 once. So 1 pops out with a remainder of 1 inside. So the best answer to this would be, because I know what 3 times 5 is, I might as well do it, 15x times the square root of 3x. And we are done. All right, I put up a set of eyeballs on here because root 80 you kind of got to be careful of. You need the biggest perfect square that goes into 80. So if you're thinking 2 times 40, no go, because this still has a 4 in it. All right, so we got to be really careful with that. If you're thinking, well, I'm going to do 8 times 10, no good, because these aren't perfect squares. So we're trying to find the biggest perfect square hiding out in there, and you might want to, somebody yell it out. Which one of these goes in? By the way, we never look past halfway, so we're looking for the biggest one this direction, because a number can't go into something more than twice, so less than twice, so we're always looking in this direction. 36 doesn't go into 80, 25 doesn't, but 16 will if you try it on your calculator. Goes in there 5 times. So I'm finding that perfect square hiding out in there. Now I'm going to clean it up. The negative stays out front. Square root of 16 is 4, pops it out. Root 5, nobody knows. Square root of x to the 5th, divide it by 2, and I get 2 that pop out, 1 that stays in. Square root of y to the 6th, 6 divided by 2 is 3, so 3 pop out, no y's stay in. It's looking ugly, so I'm going to rewrite it. I get negative 4, x squared y cubed times the square root of 5x. All right, this is so much fun. Let's move along. We are almost done. So everything up till now you did before Christmas. I apologize for the long notes. I usually try to keep them under 15 minutes, but we had final review, before Christmas review. Now we've got something new and everything's rhyming, not on purpose. All right, so how do I multiply? Well, here's the deal. It's pretty easy. When you're doing multiplication with radicals or roots, you use what I call both in, both out rule. Same with division. You can multiply everything that's outside the root. So what do I mean by that? I'm just going to go up here. 2's out, 3's out. 2 times 3 is 6. Bam. All right? I call it both out. And then multiply what is under the roots. I call it both in, both out. So on the outside, I have a 2 and a 3. On the inside, I've got 7 times 14. What's that? 98. And I've got a t and another t, which makes 3 t's. So I do what's called both in, both out. You might even want to write that right here. Both in, you can multiply, both out. You can't multiply one in, one out. What I mean is 2 root 7 doesn't become root 14 because one's in, one's out. When you're all done, you've got to make sure you simplify. So we've got to make sure we don't leave any perfect squares hiding under that root. And so right here, I've got a problem because when I take 98, which is even, obviously, and I divide it by 2, I get 49, and that should be kind of screaming to you because 49 is a perfect square. So I've got to take that 98, spot that bestie under there, one of my perfect squares. I also need to notice that the t cubed gets cleaned up as well. So now when I pop out all my perfect squares, I get a 6 because it was there. And then the square root of 49 is 7. Root 2, nobody knows, and it doesn't get better. The square root of t cubed, well, I divide it by 2. 3 divided by 2 gives me 1, remainder 1. And then I'd obviously clean that up and write that as 42t, root 2t. All right, next one up I'll do with you as well. I take what's both out, which is a negative 1 technically and a 2. I multiply them. Then I go and do what's in. A times 9a to the third is 9a to the fourth. And then I clean it up. The negative 2 hangs along for the ride. The square root of 9 I know. The square root of a to the fourth, 4 divided by 2, 2 pop out, nothing in. So really, I don't get anything left under that root. I end up with a negative 6a squared. Everything popped out. All right, so you're going to try one on your own, and then I believe, let me make sure, let me go to the next page here. Yep, then we are done. So go ahead, and I'd like this video to be paused, so who's ever running the video, go ahead and pause it. We'll have somebody try this one on their own, and then once hands are up and people are done, so go ahead and try this one and raise your hand when you're done. And once most hands are up, the sub can replay the video. So here we go. Let's begin. Both in, both out. 7 times 3 is a beautiful 21. 11 under that root is a 5 times 20, which is 100. I love that number. It's a perfect square. And then I have 1x, and 5 more x's gives me x to the 6th. Now I go simplify. I clean up what's under that root, and I pull any perfect square out. Well, this is nice because 100 is a perfect square. Its root is 10. The square root of x to the 6th, well, that's even. 6 divided by 3 is 2, which means 6 divided by 2 is 3, which means 3 x's will pop out. I kind of want to make sure you understand what's going on with that, by the way. I'm just going to go over here and put a little aside. What you're doing is using the fact that you know the square root of x squared is x, and that x to the 6th is actually 3x squareds. So this is going to pop out an x, an x, and an x. So 3 of them pop out. You really just need to divide it by 2. How many 2's are in there? So nothing's staying under the root again. I end up with a 210x cubed. Raise your hand if you had that one right. Hopefully it's all of you. All right, or most. All right, so your assignment for today is going to be the worksheet 11.2a. Have a good one, guys. Over and out.